Okay, we're starting. One thing I wanted to make sure I emphasized from last time, because I didn't want to give a misrepresentation. So we spoke about the idea of the coordinates of a vector, right? So we spoke about x is c1, v1, c2, v2, and where this was a basis, and I said that this is, so the vector c1, c2, cn is unique to x with respect to the basis. So this is to clarify from last time. So there was something that came before us. With respect to the basis, v1 to vn. All right, and I said what that allows us to do this allows us to connect v to Rn in a unique way. And so the idea was, here I have my vector space v, and here's an x. I can map that to some sort of coordinate in Rn, c1, cn, Rn. I want to just make sure that you realize that in general this is true, but me picking Rn as the example, that was only referring to this case, right? So this is true for real vector spaces. I.e., the Ci's are real numbers. Right, remember, real numbers are only one example of a field. Right? There are other examples out there. So I don't want you to think of that was in general. Here I was talking about the C's were real numbers, and so once these guys represent real numbers, I can connect that vector space to Rn. Right? But if my C's were from some other set, if they were complex numbers, for example, then it would connect to Cn, and so on and so forth. Right? So while this works in general, in principle it works in general, but when I specifically mention Rn, I don't want you to think every vector space you can connect it to Rn. That's not. I just want to make sure. In principle this works in general. Rn is the special case. In this class. Right, so everything we're studying can get more general, but in this class we always consider our scalars to be like real numbers unless otherwise specified. And that's why I could make this claim about Rn. I don't want you to think every vector space is somehow equivalent to Rn. That would not be correct to say that. So I just want to make sure that was clear. Okay. That being said, let's actually move on. So we're still talking about coordinates and bases. We're still in section 4.4.
Professor?
Yeah.
I was just wondering, and this might be completely irrelevant, but is there a standard way of organizing your vectors so that anyone who looks at a set of vectors will know that, like, oh, this one's V1, this one's V2? Or is it just the order?
You would have to do it. Like when you're setting up a problem, you need to call it a certain thing. And then everyone would have to agree. Anyone who's reading what you did, they would know what you're doing. But yes, in general, to find the coordinates and to set up an ordered pair, you need to have what you call an ordered basis, where there is some basis vector where you consider it to be the first one, and then there's another, the second one. In general, sets aren't ordered, but yes, for the purposes of doing something like a coordinate system, you do consider it an ordered basis. Right, so yeah, but that, I wouldn't say there's a standard way because the situations vary so widely, but in specific instances when you're studying something, you would label it however you want to label it, and anyone knows if they're following your research, they follow that labeling, and then everything will work. but that was actually a good question. It's a very important question that wonder, because when you're looking at coordinates, the coordinate 1, 2 is different from the coordinate 2, 1. So it would make sense to ask, does the order actually matter? I know in sets the order doesn't usually matter, but here when you're talking about coordinates of a location of something, the order would matter. And you would just impose some order on the bases, however you feel. But then everyone knows just to follow that order afterwards. So, I mean, if I'm giving you guys something to do with this, I will actually label it. I'll tell you who I consider V1, V2, V3. So I'll usually, if I'm giving you a question, I'll label it for you. Say, this is the first one, this is the second one, this is the third one. So your coordinates should go in this order. Yeah. So 4.4, continued. And so, yeah, I should probably actually mention that, what we just said. Do we have an eraser? We do not have an eraser. Forgot to bring one. In general, sets are not ordered, but for the purposes of coordinates and clarity, we may choose to impose an order on our basis vectors. If B is a basis with an imposed order, it is called an ordered basis. So in general, especially in theory, the order won't matter. Just knowing that there's some basis out there and it has this many vectors, you can do a lot of things with that. But when you really want to start getting specific and talking about descriptions of certain elements and their locations, or how you would try to map a function, then yes, you're going to want to put some sort of order on things. And you can, in general, you can choose. There's no real standard way. I give you a random basis of R3, there's nothing to say that this is the first vector and that's the second, unless I specifically tell you what that is. And let me actually run and get an eraser.
What is this?
Oh, I don't know. Let's see how far we can get with this. It's kind of annoying to use. So we're going to continue now. We're going to talk about, I'm going to do some examples here, maybe talk about dimensions a little bit as well, which is the next section. I'm not sure if I'll get the change of bases, but we're going to do some of that. I also want to, I don't remember if I gave you this notation, so I'll remind you guys. Suppose we are describing the coordinates of x with respect to the basis B. We denote this as x and subscript B. So if a basis is given and I'm saying this is a coordinate, I might, for emphasis, do that. Usually if this isn't written, it's because it's considered to be the standard basis. So in general, if I write just vector x, that means I'm thinking of the standard basis. So if x represents some vector in Rn, I'm talking about I, like in R3, I'd say that's me considering I, j, k. But if it's some other basis, I can actually label it with a subscript. So that's an important notation for you to realize. And let's do actually a small example here. So example. Let B1 be the standard basis for R2, that's Ij. B2 be this basis for R2. And B3 this basis for R2. Last time we also saw that bases are not unique in general. The same set can have several bases, and that's actually fine. Note, these are bases for R2. By the way, when I said these are bases for R2, what am I saying? What makes a set a basis for a vector space?
Spans R2 and is linearly independent.
Okay, so it means that each of those set individually span R2, and it means they're linearly independent. What does it mean to span R2?
You can make a linear combination of all the vectors in R2 using the basis.
Right, it means that any vector in R2 can be expressed as a linear combination of this one, which means, i.e., each span R2, that's 1, which means that if x is in R2, then that would mean I can write x as being equal to some real number times I plus some real number times j. Or equivalently, I can write x as some real number times this guy plus some real number times that guy. I can also write x as some real number times this guy plus some real number times that guy. Probably not all at once, but in individual cases. It is possible to construct, it's possible to always find scalars for which this is true for any x. Okay? And 2, each is linearly independent. And what does that mean? Yeah?
There's no, you can't make either of the vectors contained in this set with any of the other vectors in the set.
Okay, give me a definition of something. Less words, more math. Now the next couple of sections especially, I know we've talked about a lot of things fuzzy, but it's very important that you know definitions specifically, because when you're proving things, the mathematical definition is what's going to guide you. Yeah.
So the linear combination of the vectors in the set equals, if you set it equal to 0, it only has the trivial solution.
So this means that if C1 times I plus C2 times j equals the 0 vector, has only the trivial solution. And of course, so does if you were to do the other ones. If I took C1 times this plus C2 times that equals 0, and if I took C1 times this plus C2 times that equals 0, they all only have the trivial solution. Okay, so once we have a set that has these two properties in terms of a vector space, we say it's a basis for the vector space. And essentially what that means is we can actually build the entire vector space using these vectors. We can say the basis vectors generate the space. Anyway, I just want to make sure that When you know, and this is very important, the proofs are going to be very important coming up in the next test and so on and so forth, and for the ideas that we'll be discussing in this class. And proofs really, where you start being good at proofs is really knowing the definitions, right? So if I ask you to prove something, what you're really doing is proving that it fits some definition. So it's very important to know the definitions. So when I say a basis, you should understand what that means. And each individual thing in the basis definition, you should understand what it means separately, and so on and so forth. Okay, let's move on. I'm going to actually want you to find some coordinates for me here. For each basis, find the coordinate of the vector let's call it x equals, so here's a vector, 2, 4. i.e., find x with respect to b1, comma, x with respect to b2, comma, x with respect to b3. So let's say I asked you that question, how would you approach it?
Would you try to find the span?
What do you mean by that?
Like all the, try to add up all the bases?
I'm not sure what you mean. Ideas? Yeah?
For like B1, you move the matrix B1 vertically. You just put like 1 0 and 0 1, and then
Okay.
2 and 4, and then you solve the system using matrix.
Why would you do that? What are you after?
You want to find C1 and C2.
Okay, so that's the first thing. Again, it comes down to definitions. So in this question, I asked you to find the coordinates. You need to know, what does that mean to find the coordinates? The coordinates by definition are what? The scalars that are in front of the vectors. So when I ask you to find the coordinate of something, what I'm asking you to do is find the scalars that I need to put in front of the vectors so that the result is the vector that I'm giving you. Okay? So if I want to know what is x in terms of p1, this is just the standard basis for p1, right? It's just a standard basis. So basically what I'm saying is, how can I write 2, 4 as something times I plus something times j, right? And the C1, C2, that is going to be my vector with respect to the spaces, right? So when I'm asking you to find the coordinates of something, I'm asking you to find the scalars that you need to put in front of the bases when they're ordered a certain way. All right, and in this question, I'm actually putting the order in which I want them. So you can think of this as the first vector and the second vector and so on. So in other words, this guy here is just, this is the standard basis. So its coordinate looks exactly like itself. Okay, let's do this guy with respect to B2. So that means we need to solve, I need to say C1 times this vector plus C2 times this vector equals 2, 4. And so what that ultimately means is, yes, as he said, you're going to throw these into an augmented matrix, and you can pretty much throw them into the matrix this kind of the same way they appear. Put this here, put that the second column, put that the third column, and you're going to find the reduced row echelon form. Right? Reduce. because now the first column is your C1 column and the second column is your C2 column, and those are the guys we're searching for. Now if you reduce those here, what would this side look like? Huh? It has to look like the identity. Why? They're linearly independent. Okay, so I know that's what that's going to end up. But the other side, I actually did it, it's minus 1, 3 is what's going to end up here. Minus 1, 3. So, in other words, the coordinates according to this new basis of this guy in other words, if I take x with respect to the basis 2, it's going to be minus 1, 3. So its location in the standard basis is 2, 4. Its location in this new basis is minus 1, 3. Similarly, if I want to find this guy in respect to basis 3, what I'm going to do is I need to solve C1 times 1 minus 1 plus C2 times 0, 2 equals to 2, 4. I'll throw these into the matrix. Again, that's just me solving a system. It's a 2 by 2 system. I know it's going to end up with the identity because it's a basis, and it would have ended up with 2, 3. And so what I can write is the coordinates of this guy. Coordinates of this guy with respect to the basis 3 is 2, 3. And we're dealing with real vector spaces here over the real numbers, and so the notation is again very suggestive. And what you can kind of imagine happening is that I'm applying some sort of transformation to convert this vector, and I'm moving its position, right? And you can think of, we're going to get to that pretty soon. But there's a geometric meaning to all of this, but it's important for you to be able to, in terms of some basis for looking at the world, you should be able to like move vectors to fit. Any questions on that? So finding a coordinate is just setting up a linear combination equal to the vector and solving for the scalars in front of it. These are called the coordinates of the vector with respect to that basis. And I think here I just want to list some more examples for you. Example. We're still in the basis section. Right? Did I tell you about the standard basis for Rn and Pn? And I feel like I wrote that down. I wrote that down so many times because they also span and they're also linearly independent. They're both. So let's just make sure. E1 to En is a basis for Rn. 1x all the way up to xn is a basis for Pn, set of all polynomials of degree n or less. Another example, let's look at this one. 1, 0, 0, 0, 1 is a basis for all set of all 2 by 2 matrices.
why the subscript is n, p n is not to the power?
Oh, power usually means we're thinking in terms of coordinates. Pn here is referring to polynomials.
Okay.
So I'm just thinking of all things that look like, you know, a0 times 1 plus a1 times x plus an times x to the n. Usually when you put something to a power, you're thinking of it as coordinates and you put it in a tuple. So here's a question. And these are pretty much standard bases of three very common sets that we use. So if you want to find the basis for a set of matrices of a certain size, it's just a list of all the matrices where it has 1 in each component and zeros everywhere else. And you sort of do it in a certain order and you'll actually get a basis for that automatically. Here's a question though. In terms of the basis in example 3, what is the coordinate of this matrix?
Could you repeat the steps from earlier?
Okay, so what would we have to do?
Could we take the first matrix, 1, 0, 0, 0, and then
Yeah.
What is this like C1B1, C2B2, C3B, C3B?
Yeah, same thing that we did before. By definition, to find the coordinates of something, it means you set up coefficients in front of all the basis vectors, you add them all together, set it equal to the thing. Just because the thing happens to be a matrix doesn't change the definition. So that is, we need to solve C1 times this guy plus C2 times this guy plus C3 times this plus C4 times this equals 1, 2, minus 1, 3. So this would mean, well, it's the standard basis, so it should be easy to read off. That's why we make things the standard.
why is there a 0 there?
0
The first one here.
here. I'm so used to writing the identity. Yeah, it should have 1 and 0, 0. So what would that mean? So this guy with respect to, I don't know, let's call this something S3. Call this S2. So with respect to S3, I can think of it as a coordinate. And what's the coordinate going to be?
1, 2, negative
1, comma 2, comma minus 1, comma 3. By the way, if you're typing, if you wanted to check your work in like Wolfram Alpha or something like that, how you would type this matrix is pretty much like that. You type the first row, comma, and then you put the second row. Right? You would actually list them in a line like this. So that's how you would type a matrix in computer language. And I believe in MATLAB it's similar, except you use brackets. So you can actually type something like this, and the computer interprets it like that. And when the computer is moving matrices around, it's really just moving coordinates around, which is already very good at. So that would be the coordinate of this matrix. Meaning, if I'm doing something in the land of matrices that's particularly difficult in the land of matrices, but it's a lot easier to do in Rn, I can just translate all matrices to these vectors, right? So 2 by 2 matrices, a 2 by 2 matrix, I can translate to a vector in R4, do whatever I need to do in R4, and then translate the answer back. Hopefully that's clear. What else? I have an example here, but I'm not sure why I wanted to do an extra one. Am I going to use that later? I guess I could just write it down. When you see something in multiple contexts, it makes it nicer. So, another example, we saw that S equals 1 minus 1 minus 2. Is a basis for R3. If I consider R3 a vector space with the standard operations, find 1, 2, 3. With respect to X. What do we do here? There's something that we need to solve.
The augmented system.
Okay, which system?
1, 2, 0, negative 1, 1, 0, 1, 2, 0, 1, sorry.
-2.
Negative 2, 1, 1, 3, I'm way out.
2, 1, 1, 3, 2. You need to solve that system because that's going to tell you what the coefficient of C1, C2, C3 are. Ultimately, if you reduce this, the fact that it's a basis means if you're doing by hand and you know that it's a basis, you definitely should get the identity here. So if you don't, you made a mistake somewhere. And I think it was minus 1, 1, 0. So 1, 2, 3 with respect to the basis S is minus 1, 1, 0. And we'll discuss some more about bases and why something like that is useful, but for now, let's actually, the main thing I wanted to talk about today was dimensions. And this is mostly going to be just some definitions and thoughts and ideas that I want rattling around your heads and mulling over until the next time we're going to be using it. And we'll revisit things like this, calculations like this when we talk about change of bases. But for now, let's talk about dimensions. Definition. I was going to tell you what the dimension is. let V be a vector space. The dimension of V, denoted DIMV, is defined to be the number of vectors in any basis for V. If a basis has a finite number of vectors, V is called finite dimensional. And we write the dimension of V equals n, where n equals the number of basis vectors. Otherwise, V is called infinite dimensional. So that's our definition for the dimensions of a vector space. So for example, Rn is what's the dimensions of Rn? We can call it n-dimensional. i.e., the dimension, we can write that in notation, of Rn equals n. What about, what if I ask you, what is the dimension of Pn? Plus 1. Notice that in the basis vectors for Pn is going to be the set 1, x, x squared, da da da, up to xn. There are n plus 1 things. Right? Because there's the guy for x to the 0, x to the 1, x to the 2, up to n. So you're counting from 0 to n, there are n plus 1 things that you would count. What about the dimensions of the set of m by n matrices? So a matrix with m rows and n columns. Mn. So if I have a 3 by 5 matrix, the set of all 3 by 5 matrices, if I take them together, they form a vector space. How many vectors would be in the basis vector? It would be 3 times 5. It would be 15 matrices in its basis. So those are examples, by the way. Note. I just gave you a dimension, a definition in terms of the number of basis vectors in a basis. If that definition is to be like a well-defined definition, what is something that would have to be true? Can you guys think of a fact that would have to be true?
They have to be linearly independent.
Oh, I define the dimension of a vector space based on the number of vectors in the basis. What's a possible issue here?
more dimensions than vectors.
So we know what a basis is.
It has to actually be a basis.
Sure, we know what a basis is. It's a set of vectors that span the set and are linearly independent. Yeah?
Every basis must have the same number of vectors.
You would have to have the same number of vectors. Remember, bases aren't unique in general. So we can say, someone can say, oh, the dimension of this is n plus 1 because with this basis there are n plus 1 things. And someone could say, well, I could make up another basis for the set of polynomials. But would it have the same number of things in it, right? Well, according to the definition, it better have the same number of things in it. Because if I have one basis over here that has 3 vectors, and I have another basis for the same set that has 5 vectors, is the dimension 3 or is the dimension 5? I can't define something if the answer can change, right? So it turns out, for this dimension to even make sense, the number of basis vectors in any basis you can come up with have to have the same number of things. Yeah?
Yeah, but wouldn't basically have to equal the number of vectors R equals to n in order to be a basis in the first place?
You're talking about in Rn? Are you talking about in Rn?
Yeah.
Well, yeah, because of what we just said. And that's kind of the fact here that any basis of V, let's say it's finite dimensional, must have the same number of basis vectors. Right, so sure I can think of Rn as having like the standard basis vectors, E1, all the way up to En. But if you come up with another basis for Rn, it should have the same number of vectors. And that's the only way I can make this definition. That's fact 1. Fact 2, and this is, you can kind of think of why fact 1 needs to be true. Is the following. We looked at 2 things. We notice here that suppose there are 2 facts that we mentioned before. Suppose S is the set V1 VR, I'm using R here, and V, the dimension of V, then if R is less than N, we could have made a conclusion. Do you guys remember what conclusion we could make if R was less than N? Yeah?
It can't span.
It can, then S does not span. We actually saw that, if not last lecture, a couple lectures ago. And if R was bigger than N,
It's not.
then S is not linearly independent. Basically, under these 2 situations, if you throw everything in a huge matrix and you find the reducer echelon form, this side, the left side wouldn't reduce to the identity, and you wouldn't be able to get them to be linearly independent. And this side, you would have an infinite number of solutions to you will have a vector that you cannot actually solve for. Right? So the idea is, if I have less vectors than the dimension, it's a problem. If I have more vectors than the dimension, it's a problem. Meaning that any set that both spans and is linearly independent, it would have to actually be equal to n. And it would have no other choice. So that's a nice fact. And that leads us to the definition of dimension.
I have a question.
Yeah.
What happens if R is greater than N, you're saying it's not linearly independent. In that case, would it be undefined?
Not linearly independent means if I set up that equation and set it equal to the zero vector, it doesn't have the trivial solution. It has solutions other than the trivial.
So it would have infinite solutions.
Yes, it would have infinite solutions, which means that there's at least one vector that can be represented as a linear combination of the other vectors, and so it's redundant. Yeah, so it's good for you to think of these phrases as in terms of the mathematical definitions, right? And then you can talk about what they mean afterwards. What else do I want to tell you about dimensions? Something we can also talk about, and this will be important later. We can also talk about the dimensions of the solution set to a system. This is going to be important later. We're going to use this when we start thinking of matrices as linear transformations. We're going to make use of this fact. So here's an example. Find a basis for the solution set, and hence the dimension of solution set to the system. And I have a system. W plus 2x plus 2y minus 3z equals 0. 2w plus 4x plus 2y minus 4z equals 0. Minus 4w minus 8x minus 8y plus 12z equals 0. 3w plus 6x minus 3z equals 0. So here's a homogeneous system. Basically, I want you to find the solution to this thing and determine its basis and dimension. And then I'll mention why it even makes sense to access the customer. Okay, so how would you go about doing this? Let's see what we remember. It is something that we're going to have to do in the next test. So I can give you a system and I can talk about finding a basis for the solution set of the system. Yeah? So you'd augment the matrix. So that would be step one. Augment. So we would have 1, 2, 2, minus 3, 0. We would have 2, 4, 2, minus 4, 0, minus 4, minus 8, minus 8, 12, 0, 3, 6, 0, minus 3, 0. Then we'd find the reducer echelon. So you do a bunch of row operations to get into the nice form. In this case, I did it for you, but then after this, you guys are going to help me figure out the answer. So it's 1, 2, 0, minus 1, 0, 0, 0, 1, minus 1, and then 2 rows of zeros. So this could be a question on a test, for example. It's an important thing to be able to do. So I can give you a set of equations, ask you to talk about the solution set, not just find the solution, but also find a basis for the solution and its dimension. What you would do is you'd actually just solve the system as you would usually. So when you get to this point, what do you do? How do you find the solution?
Whichever variable doesn't have a pivot is a free variable. Whichever variable doesn't have a pivot is a free variable.
So it's very important that you remember that. So first you identify the pivots, and then describe which variables do not have pivots. So you remember that this is the x column, or the w column. This is the x, y, z. So my w and my y has pivots, my x and my z does not. So this would mean I would set, you can set them to be themselves, but let's just set x equals t and z equals r, or whatever. And so what do you do next? Yeah?
Find the other two.
Yeah,
Based on
what do you
those.
do?
Okay. So, y is equal to z, which is r.
Okay, remember you go from the bottom row up, so that's just 0, that's just 0. Here's where you, the first row you get some information from. From this one you said y minus z equals 0, which means that y equals z equals r. Okay. Then you move one row up. So this comes from row 2. And now you go to row 1. And row 1 tells you that w plus 2x minus z equals 0. Now x we call t. And so w would be r minus 2t, right? And so now how would I write this solution? Yeah?
The vector r minus 2t, then row.
Well, you should write w, x, y, z equals, what, your w is this, so you just
Yeah.
do a matrix equality kind of thing. R minus 2t, x,
T.
x was just t, y was r, and z was r. And then you kind of split those guys up in terms of the variables, right? So we want the constant term, which is just 0, plus all the guys times r, plus all the guys times t. And so in the r vector, we would have 1, 0, 1, 1.
Isn't it 4 0?
4 zeros. And in the t, we would have minus 2, 1, 0, 0. Okay. Now remember, every homogeneous system has a solution. In fact, we also always know is always solution to the homogeneous.
0, 0.
But it's possible to have other solutions. In this case, we had other solutions. In fact, we have infinitely many solutions here because I can vary the values of r and t and get different sets of solutions. So now, what I just did was I found essentially those two vectors that have the parameters are the basis for the solution set. Why? Because my solution is a linear combination of those vectors. So, note the solution. W, X, Y, Z is a linear combo of the vectors 1, 0, 1, 1 and minus 2, 1, 0, 0. This means a basis for the solution set is the set of these two vectors. Which also means the dimension of the solution set is two. There are two basis vectors, so the dimensions is 2. Yes.
Why we don't add the 0, 0, 0?
Because 0 plus anything is just itself. Like, it wouldn't matter if I wrote that or not. Right? If I add 0 to these guys, it's...
If 0 were in this set, it would be 3, the dimension would be 2.
Can I put 0 in this set?
Oh.
No, once the 0 vector is in a set, it's not linearly independent. So the 0 is not a vector you put in the set. Now it's worth making some comments about this guy. What do we know about the solution of a homogeneous system, the solution space? Solution set. Huh? Sure, but I mean the solution set. If I look at the set of all solutions, what do I know about it? It's always 0? No.
It's greater than 1.
Well, one thing is I just found a basis for it. So what does that tell you what it is? It's a vector space. This means, and we've seen before, the solution set is a vector space. We call it the solution space. If our system is homogeneous, the solution space, which we know is a vector space, is called the null space of the system. AKA. And really what we call it kind of depends on the context that we're thinking about. So if you're thinking it in terms of solutions to a system of equations and it happens to be homogeneous, I call it a null space. If I'm thinking of the matrix that I'm dealing with as a function, a linear transformation, I call it the kernel, aka null space equals kernel. And that's a word that I spoke to you about. The difference in the names really depends on the context. Yeah?
From the reduced row echelon form of matrix, we could immediately tell the dimension of the solution space.
Yeah. And note, dimension of solution space equals, how did you tell the number?
The square matrix, you'd have, your n by n matrix, and I would say n minus the number of pivots.
Yeah, well, the number of free variables.
Right.
It is also called n minus the number of pivots. There's a whole theorem about that as well. Yes.
I'm wondering if you could immediately write down the standard basis for the solution space based on free variables.
What do you mean the standard basis?
Well, standard basis would just be 1 in whatever position occupied by, so I would think you would write something like, standard basis for the solution space would be the set of vectors 0, 1, 0, 0, and the vector 0, 0, 0, 1. Like what I'm arguing is that there's some sort of transformation between the basis that we.
I probably wouldn't phrase it that way, because there's a standard basis for Rn, you know this, right? But whenever you're talking about, for example, a solution to a system like this, the solution space is actually a subspace of Rn. And to talk about the standard basis of a subspace is kind of a weird thing. You could, in general, like, I guess, vary what the values of these guys are to get things in a nicer form, but you don't really talk about the standard basis of a subspace, really. If I guess you can talk about the space, if we're thinking of everything in terms of Rn, then what this does is it spans a plane, right? Now, to say that that plane is R2 might not be exactly correct, because it might not be R2, right? So, for example, if we're in the three space, right? R2, and this is X, Y, Z. If we're in 3 space, R2 is considered to be the floor, right? But there are other possible planes out there, right? I can talk about the solution space as 2-dimensional, so I can think of it as some plane, but it might not be the standard R2 plane, and the standard R2 plane is the guy that has the standard basis.
But the only difference between that, whatever plane we might not call R2 and R2
is a change of basis,
yeah.
which is the next section. Yeah. Right, but you wouldn't say there's some standard way of representing that guy. The standard way would be to think of it as R2, but you have to have the idea that it's not exactly R2. It's a 2-dimensional space, but it's not exactly R2. It might be some other plane. It's some other plane that passes through the origin for sure, but all its points might not line up with R2. In fact, this guy's a 4-dimensional vector, so saying it's R2 presents other challenges. R2 we know has two coordinates. So there's a lot of things going on here. It's not exactly right to say that we can find a standard basis for this. But that is something that you can note here. You can note that the equations that we're looking at lived in R4, but the solution space is in R2. Meaning that the vectors that will solve this system are all the vectors that live in a 2-dimensional plane that lives inside of R4. And it might not be the R2 plane, it's just some other plane that passes through the origin of R4. And if for some reason, I guess your concern about using the standard basis is the fact that maybe you want calculations to work out similarly or easier, or to somehow translate things, or
Just wondering how sort of obvious it is from the sort of structure of the reduced row echelon.
it's not obvious at all.
It's not obvious what the,
It's not obvious at all. You can obviously tell the dimensions, and you can obviously tell the number of basis vectors. But as for whether they happen to fit a certain form that is aesthetic to you or convenient to you, there's nothing like that. Yeah. And if, for example, you don't find this aesthetic and it's difficult to work with this, you can use a change of basis to put it into a more convenient form for you. Do whatever you need to do, and then change it back. Right, so it's sort of, and that's where the things where I'm asking you to find different coordinates comes in, right? You go here, you're like, okay, it looks like a plane, it's kind of like R2, but it's not really R2. I'd like to work in R2 because I know how to do everything in R2. What I would do is I would change these coordinates to equivalent coordinates in R2, play around with those coordinates, and then change it back. Right, but as for saying it's not right to say the standard. We'll stop there, and we'll pick up next time. So for now, we're still looking at a lot of ideas. We'll do more calculations coming down the road.